Hello everyone. So last time we talked about the periodic table, the history of it, how the elements are arranged. Today we're going to talk about some patterns that we notice on it. So to start off, we're going to talk about the atomic radius. To begin, the atomic radius is defined as the distance between two nuclei when two of the same atoms are bonded together, and that distance is divided by 2. So here we have an example of hydrogen 2, the molecule of hydrogen. The atomic radius of hydrogen would just be the distance between two nuclei of hydrogen. So when we talk about the atomic radius and the trend within the periodic table, when we're going down the group, the atomic radius is going to increase. Our atoms get bigger as we go down the group. This is because we're adding electrons. We're adding more and more energy levels as we pack in those electrons. So naturally, adding more energy levels and more electrons means a bigger atom. Another reason why the atom gets bigger as we go across is due to an effect called shielding. So as the energy levels are increasing, there are more and more electrons being packed in. Now, the nucleus being positively charged and the electrons being negatively charged, there's actually an attraction between the two. The valence electrons, the electrons on the outermost ring, are also attracted to the nucleus here. If there's more inner electrons to get in the way, there's more shielding. The valence electrons on the outside are being shielded more or protected against the attraction. So the more energy levels, the more shielding there is, which contributes to why going down the group increases the size of the atom. So essentially, the bigger the atom, the more shielding, making that attraction between nucleus and electron more difficult. Now, when we go across a period, the atomic radius is going to decrease. This is because the number of energy levels within the atom remains constant. So in our example here, we've got lithium, nitrogen, oxygen, fluorine. They're all located on row 2, or energy level 2 of the periodic table. But as the number of protons in the nucleus increases and the number of electrons, there's more attraction going on between the outer shell electrons and the nucleus. So with more attraction, that's what kind of brings everything closer together. Hence why the atomic radius is going to decrease. Because these electrons are getting closer and closer to the nucleus, the size of the atom should shrink. There's less shielding going on here. So the outer shell electrons are being pulled closer as we go across because there's more protons, same energy level, so the atom is going to get smaller when we go across the periodic table. Now, before we get to our next term, we have to first discuss ions. Ions are defined as an atom with a positive or negative charge to them. We have two types of ions, the cation and the anion. The cation is positively charged. They're formed when a neutral atom loses electrons. Essentially, the number of protons is then greater than the number of electrons, so you're going to have a positive charge overall. Metals are the ones that form cations, and the charge of the cation is determined by the number of electrons lost. For example, magnesium, if magnesium loses 2 electrons, it has a +2 charge. If sodium loses 1 electron, it has a +1 charge, which we just denote with a plus sign. On the other hand, an anion is an atom with a negative charge to it. This is when a neutral atom gains electrons, so then the number of electrons is greater than the number of protons. Nonmetals are the ones that form anions. They're the ones that want to gain electrons. And again here, the inverse of the cation, the charge is written by the number of electrons gained. So fluorine, who wants to gain 1 electron, takes a charge of -1. Oxygen, which gains 2 electrons, takes a charge of -2. Okay, so an ion is nothing but a positive or negative charged atom, which is caused by either the gaining or losing of electrons. We'll come back to ions a little bit later in the year, but knowing that atoms can gain and lose electrons is imperative for our next part. So we're going to get into what's called the ionic radius. So the ionic radius of an atom similar to the atomic radius, except we're talking about ions here, meaning we have lost or gained electrons. Within a cation, an electron is lost. So this outer shell electron goes away. Because that outer shell electron, that valence electron, is lost, the overall size of the atom decreases. So we say that a cation is smaller than the neutral atom version of it. So if we take a look here between sodium and the sodium plus 1 ion, because this valence electron left, the sodium plus 1 ion has one less energy level to really consider within its ion, so it's going to be a little bit smaller. Conversely, the anion, you are adding an electron to it. So because an electron is getting added, that energy level is going to get a little bit more spread out. The electrons want to separate from themselves because now you're cramming more into there. So the anion is actually going to get bigger. So a cation is smaller than the neutral atom version of itself, but an anion is bigger than the neutral atom. It really depends on if you're going to add an electron or if you're going to subtract an electron. So if you're subtracting an electron, you're taking it away, it should get smaller. If you're adding an electron, it should get bigger. So we're going to talk about a term here called ionization energy. So the ionization energy is defined as the energy required to remove an electron. We can show it by this equation here, just an example here. When sodium loses an electron, it forms the sodium plus 1 ion and an electron. The ionization energy is the energy required to pull it off, and energy is needed because of the fact that there's attraction to the nucleus. So you have to put in some effort to pull away the electron. As you remove more and more electrons, more energy is needed because the atom is going to fight harder to not lose electrons. Thus, as the energy levels increase, the ionization energy levels increase, the amount of energy needed is going to increase as well. So the first ionization energy is actually lower than the second, which is lower than the third, and so on. Now, when we go down a group, again, we're going to focus on the attraction to the nucleus here, because that determines how easy or hard it's going to be to remove an electron. If there's more shielding, more protection between electrons, then it's going to be easier to pluck off, meaning less energy. So as you go down the group, the ionization energy is going to decrease because there's more shielding, so there's less attraction, making it easier to pluck off those electrons. Now, if we talk about going across the periodic table, this ionization energy is going to increase because there's more attraction to the nucleus. Again, the number of energy levels, the shielding is going to remain consistent. But as the attraction increases because the number of protons are increasing, there's going to be more attraction, so it's going to take more energy to remove the electrons. So across the period, the ionization energy is going to increase. And again, as electrons are being removed, the element itself is getting closer and closer to becoming the noble gas, which is essentially the goal for every element here. So as they get closer to becoming a noble gas, it's going to be harder to pluck away electrons. When an element actually does have that same noble gas configuration, it's going to take so much energy to pluck it off. So as elements and atoms remove electrons, those ionization energies, essentially the number of electrons you removed, are going to take more and more energy with every subsequent electron relieved. And then the last term to kind of go over is what's called electronegativity. This is the desire for an atom to gain an electron. You can show this with kind of the opposite equation shown for ionization energy, because it is the opposite. By this example here with fluorine, fluorine gains an electron, it becomes a fluorine anion, fluoride. Now, the value here is not really an energy value. It's not something that you can just kind of measure. It's more calculated value using what's called the Pauling scale. The Pauling scale ranges from 0.7 to 4.0. 0.7 is the lowest calculated value here. 4.0 is the highest calculated value. So going down the group, the electronegativity, the desire to gain electrons is going to decrease because there is less attraction to any electrons on the outside. So all of these terms deal with attraction to the nucleus here. How likely is it to remove an electron but in this case, how likely is it to gain an electron here? So if there's less attraction, there's going to be less desire to gain an electron. There's no point in gaining an electron if it's not that attracted to it. So when you're going down the group, because there's more shielding between the nucleus and the electrons here, that electronegativity, that desire to gain electrons, will decrease. When we talk about going across the period, there's more attraction because, again, the shielding is constant. So because there's this more attraction going across, the electronegativity will increase here. So going across, electronegativity, the desire to gain an electron, is going to increase because of the fact it's getting smaller, there's more and more attraction. You can also think of it as an atom's getting closer to 8 valence electrons, the noble gas number of electrons, of valence electrons, they're going to want it more. Fluorine, who only needs 1 more valence electron, is going to want that last electron so much more than something like nitrogen, which needs 3 more. So that's another way to look at it, to consider which element is going to have a higher electronegativity.